So we're going to be covering arrays today, ending up with this kind of animation, building on a little bit of the techniques from the previous weeks. If you remember, we were doing some things, drawing lines, just using the add vertex, add prim functions and stuff like that. So maybe week 7, we did a bit of line drawing, and then we also ended up using arrays to manage the individual threads that we were going to be drawing. So just a refresher on arrays, and then also building on, not this one, but some of the line drawing, line building techniques as well. JonasJ.com, how's it going? So just getting into arrays here, I wanted to do a little bit of an overview or a refresher, depending on whether you've seen them or not before. So array, you could think of it like a list of data, and you can have an array of any type of data. So if we remember when we introduced the matrices, and one thing I was doing with the previous files, there's links to them on the YouTube channel. If you just do !YouTube in the chat, you'll get a list to or you'll get a link to my channel that has a playlist for these VEX. So we just pop open the matrix. I ended up making a pretty nice visualizer inside of that file for looking at the row column construction of a matrix. Just give our boy another second to fire open here. So when you think about a matrix, we were using it to store transforms and stuff like that. But you could also think of a matrix kind of like an array. So this was the visualizer that I made here, and then this is visualizing the transform that it's producing. But if you've ever inspected either with kineffects or packed primitives, or even, let's just use this, orient along curve. Oof, got a crash. Sorry about that. Not starting off well. We'll just do it in here. So we got a circle, and we'll turn this into a curve or into a line by just setting it to an open arc like this. And then if we want to use the orientation along curve, this is like a node that's built to do what we were doing in the previous week. We were building a local frame, local space coordinate system for the curve. And if you want this to output a matrix, you can just uncheck the traditional up and n. This is like the tangent, bitangent stuff that we were building last week. If you want to directly build the entire matrix yourself without having to include or use the axes to build it, you can just check here to output 3x3 transform. And then if we look at in the geometry spreadsheet how this is constructed, you can see transform, and then in the brackets is 0, 1, 2, 3, 4, 5, 6, 7, 8. So the way that they store matrices 3x3 is you could think about it as an array. It just has 9 slots to fill. So even though we visualize it, let me just get that last file open again. Even though we visualize it using the big brackets with row column formation, that's just more for mathematical reasons and like formulas and stuff. People visualize it in the row column. But the way that the computer interprets it, or the way that it thinks about it, is using an array. So array is just an arbitrary length list of data. And you could use it to store, this is just storing floats. You could use it to store, get back here. So the way that the computer, the way that humans will usually describe like a 4x4 matrix in this case, is using these brackets. Let's just resize some windows. So this was our transform, and then visualizing it as a matrix, you can see that our numbers update, and like row, column, diagonal, these mean specific stuff for humans. That's the way that people kind of keep track of it like this. But for the computer, it just thinks of it as a long list, in this case, 16 individual float numbers. So even though we haven't technically used the array data type, matrix is kind of a array. Even something like a vector that has x, y, and z coordinates, this is also a type of array you could think of. So it's like 0, 1, and 2 for an x, y, and z position. So that's kind of an array of dimensions. You have like 3 floats, and each one is describing a different dimension. So if we look down here, this is just a grid, and then I'm running Wrangle over the primitives of it. And what I've done here is declared a new array that's going to be just called colors. And then using these curly brackets, you can define the list of colors that you want to fill your array with. And then let me just build this out so you can see a little bit easier what's going on. This, when we refer back to it, is just used to choose which item of the array that you've placed in it. So I have red, like 100, CN, or 011. Got a yellow kind of color, and then we got the last one that's this purple, magenta, whatever you want to think of it as. Then we keep going on, like we don't have a 4th entry, so it just gives us a black color, or just fills it like that. So one thing that you can use that's pretty handy is the len function. So this stands for length. It's only for array lengths. So if you want to know how many items are in an array, you can use this function. And then this is also similar to how computers, like the difference of how computers count and humans count. So by default, this is probably telling us 4. We could even double check here if we just add a debugging attribute. And it doesn't want us to do this. And then we need to look at the primitives. So this is telling us 4, but the computer counts these as like 0, 1, 2, 3. So we would just need to do -1, and then we're referring to the last element of the array. Like that. You would kind of count backwards from the end that way. And then if we just go back to what I originally had typed in here, like I don't have it in my clipboard anymore. But basically, I was generating a random number per element, or in this case, per primitive. And then this will give you, we've used it before many times, and it will generate random numbers between 0 and 1. So this is giving me the green Microsoft Word kind of style spelling mistake, because I'm generating a float that's a number between 0 and 1, and then I'm trying to use that as an index to retrieve a color from my array. So it's saying you're messing up because you're giving me, like, you want to get a book from a bookshelf and you say give me the 3rd one from the end or something, it makes sense. But if you say give me the 2.5 book from the end of the shelf, is kind of a mess. So if we do just something like floor, this will round down to the nearest whole number, or the nearest integer number. We no longer get that error. But because we're just generating numbers between 0 and 1, the floor function here will just always round down to 0. So if we scale this or multiply it by the length of the array, then we're automatically going to scale it, or our random number will always refer to a random number expanded to the entire length of the array, if that makes sense. So these are nice if you want to use like a more restrictive color palette. You're used to the way that random colors are generated in Houdini. It just generates random numbers between 0 and 1 for R, G, and B. So you get pretty, it just has a kind of look to it, and it's not the way that color palettes typically work. It's just pure random colors. So if we try it here and just give us a random color, like that. This is kind of a default look. It's just has a certain look to it or whatever. So if you want to just have a little bit more control over your color palettes and color selections, you could manage it like this. Some people will also create ramps on the bottom of their wrangles or in other softwares and stuff like that. And the way that it works is similar to an array. You just make a list of keys or entries into your ramp, and then those are compiled into a list, kind of like this. So hopefully that's a little bit better of a kind of way you could think about it. Like an array, you're kind of like putting a bunch of index cards into a box, where it's just like a library or a little collection of numbers or of variables, if that makes sense. So we can also make an array the same way like this. If I get rid of my offset here, should see that the results are exactly the same. So instead of using the curly brackets, we're just using the set function and then this array function to construct or to build our array like this. This is the same way as if you're making, just say, blue. So if we're making the color blue, we could make it using these curly brackets like this. And we could put it, just add it to the end like that. Or you can also use the set function like that. So both of those give you the same results, but the reason people use these set functions is because you can use variables in your declarations. So if we want our blue to be a random intensity or luminance, we can use the random function inside of our like variable construction here. If we do random from the element number, and then I'm just going to do a different seed or different offset. And then each time we construct this array for each primitive, it will give us a slightly different intensity of blue. That makes sense. So the set function allows you to do that, but the curly brackets doesn't allow you to do that. You can't use variables, you can't use functions or any of that fancy stuff inside of these Egyptian brackets. You can only do the constant numbers. So if we go into the other thing here, we try to do a similar thing. The array construction will fail as well. So this would be why people would use the set function. How many sets of array we can have in vector color? You can have as many as you want. I imagine you might fill it up at some point, but you would probably break your fingers typing out that many colors before it failed. You just get rid of this. We'll go back to set. No limits, yeah. I mean, I would consider it unlimited. There's probably a limit in memory or like the compiler will break at some point. But yeah, this is a good way to do it. If you want, sometimes people will split these declarations up into multiple lines if you really need to manage a bunch of it. So 68 million, is that you've actually looked it up and that's the confirmed amount? So if we make a new line here, because this code isn't white space sensitive, it's only looking at the semicolon to end its function or its line of code. You can split it up like this and the code will still work. So if I wanted to make a really long list of colors or a big array, you could fill things this way. You don't have to do as much like horizontal scrolling and stuff like that. Kind of making weird colors here. But you get the idea. If you want to manage it, this is just a different kind of style that people will use. So the compiler ignores these new lines in your code, and it will just view this all as one line of code. But instead of having to do this kind of unfortunate scrolling, you get the idea. It's just some people don't like to do it. So this is probably a lot harder to read than it was when it was like stacked before. And then if we just want to get back to, I don't know, I probably messed this up quite a bit, but you get the ideas. I was going to keep these the same, but I think it's okay. So another thing we can do to give us the same results as our first method is another way to work with arrays. And this is just using the square brackets. This is basically referring to the item number or the element number that you want to add your entry into. So the array will automatically get resized to accommodate these elements, if that makes sense. If we go like 5, then the numbers between 2 and 5 will just get initialized to black or to 0. And if you want to overwrite something, you can do it that way as well. So if I wanted to take 2, which we originally had here as yellow, we want to set it to white. We can do that and then overwrite that existing entry or the existing element in the array. So far, these are all just different ways to accomplish the same thing or to propagate an array. And then again, this is another method. Same results. We're just using the set comp function. It stands for set component. You can use it this way. And then at the bottom here, you can see I've used get comp instead of the square bracket notation or the square brackets method. And then this last one uses some special kind of function called push that will automatically expand your array by 1 entry and then add this to the end of the array. So if you look at the side effects documentation, they do a pretty good job here. Not as visual as what I did breaking down everything, but it's a good reference point. And you can see here that we were just using vectors for colors, but you can make an array with any data type. You can even have an array of matrices, I believe. And then here are the different functions that I was referring to. So we'll get a little bit more advanced here and take a look at how we could use arrays to do something a little bit more interesting. So if we take a grid, before I do this, let me do a share of the file so everyone's up to date. Julian, how's it going? We'll make a new scene. This will be week 8 array. Start. All right. So that's getting started, just different ways to create arrays and fill them with values, and then also access or retrieve numbers from them. So right now we've just created like kind of our own little library or subset of variables we want to use. We can do something a little bit more complex with arrays. So I'm going to make another grid here, and then I'm going to make a single point, which have one point at the origin. We can move it around a little bit if we want. And then we'll do a wrangle and wire it up like this, with our grid in the second input and then our point in the first one. And then the code or the function we're going to use is called near points. I'm just going to call my variable the same thing for clarity. So the near points function will let you get a list or an array of all the closest points on a geometry. So if we use it here, we just type in 1 to say the auxiliary input. And the next is the query position, or just the nearest points. So we want to say the nearest points from my current point position. And then I think the next one is the maximum distance, so like 25 units. And then the next number is how many we want to limit ourselves to be finding. We could start with 3. And it's going to cause a problem here at the start. So when I do my near points function, my near points variable, I just need to add these brackets. This will indicate that you want to create an array data type. So like up here, I was doing the same thing. So we have a list of the nearest points. If I want to debug it, you can make an array attribute on the geometry like this. I'm just going to use capital N and set it to the near points. Then we just go over to the points. So if we look at our grid, we turn on point numbers, and I don't know if there's a good way to kind of see that. We'll make it better in a little bit. We're basically telling this point where the nearest point numbers are on the grid, or whatever geometry we attach to this. So if we want to make this visualization a little bit better, we can draw connections to the nearest points. So we'll use the for each function. And then this is what we ended up using at the end of last week. It got a little tricky. Basically, this will iterate over each item or each element in your array. So in this case, we have, this keeps, oh no, we crashed. All right, let me get back here. It doesn't like sometimes when I comment out and do silly things with the code as I'm explaining it sometimes. The VEX doesn't like me. All right, we're back. Somehow my UI didn't get set properly. We try to get us back at the full visibility. All right, we're back with the big font. So the for each function is going to loop over or run over each entry of the array. So I'm just going to go back to full screen. And we look at our spreadsheet here. We have 3 items in the array, or 3 point numbers. So the for each will run over or iterate over each element. And I'm going to say integer pt and near points. So see if it works. All right, it didn't crash. So this pt will become the current item or the current element of the array. So in this case, it's the nearest point number, or the pt for point. And then if we wanted to draw our line, we can do that inside of this code. Just say int line equals add trim 0 for our self or the current geometry, and then polyline for the type of primitive. And then we just need to do our add vertex. So we'll start with the current point right here. So say add vertex to the current geometry, or again, it's 0. The primitive we want to add the vertex to is the line. And then the point that the vertex will be attaching is going to be our current point number. So when I did that, you could see in the viewport, the point goes away. It's still there, but because it's connected or parented or belonging to a line or a primitive, you no longer see it. It's like the same thing when you make a line like this, and it doesn't have a length. It just looks invisible. So if we want to actually see the line, we'll add the end point or the next connection. We need to get the end point. That this is going to be the end position, I guess is a little bit more clear. And we'll get that from the geometry. So we can use the point function. We're going to use 1 for this auxiliary geometry, and we want to get the point or the position attribute. And then usually I'm always using like at ptnum. This would be getting the current point number from this input. but in this case, we want to use it with our PT. So we're going to be filling it with one of these three point numbers or elements each time this loop runs. And then we just need to add the vertex. Too many brackets. We'll do another 0 for this current geometry or this input ourselves, basically. A line again to add it to the same primitive. And then we don't have the end point number, or we don't have the end point. So we can make it using the add points function. So again, this one we put 0 for ourselves, and then the next is the position to add the point. So we'll say the end position. Ah, it worked. All right. Let's get our display back up. This is complicated. Arrays get pretty complicated. Yeah, it's a lot of stuff to manage the way that they work. This is kind of the most difficult or the most technical data type in VEX, but it can be pretty powerful. So we don't want to take just 3 points. We could increase our limit here to 13, and then we create lines for 13, the nearest 13 points. I'm always lost in VEX. Yeah, it takes a while. I don't know. I found it's a lot of trial and error. You kind of have to keep on it too. Like, usually I'll challenge myself to do something in VEX if I have the spare time or I'm just messing around, instead of doing it if I know a more easier way, or like if I was used to using the VOPs quite a bit. Arrays in VEX are actually a lot easier than arrays in VOPs, so that's a bit of a benefit as well. If you guys ever use the arrays inside of here, it's a little bit more of a mess. I wouldn't really recommend using arrays inside of VOPs. If you don't do it every day, you forget. Yeah, when you're building the knowledge, you kind of have to keep on it. Once you kind of have the skill set built, and once you've used it enough, I find it gets easier, especially because you'll have older scenes, and like you'll be able to kind of kit bash like pieces of code and keep reusing them. So for example, like this step I did here, building the line, once you do this pretty often, it gets easier to think about and everything. So hopefully that encourages you, or is a glimmer of light at the end of the tunnel. So if we take this first, or this, I guess it's the second, like 0, 1, 2, this argument right here, this is the maximum distance to find near points in. So if I just set this to 1, we've said find at most 13 points, but only look at a maximum radius or maximum distance of 1 unit. So if you want to, sometimes you just set this to like a really big number, and then you're unlimited. Never know what to do when sims are running, so I use VEX will pass the time. This is a good practice. It's a good thing to do if you're this stuff I'm doing doesn't take a ton of resources, like computer resources, but it's good little kind of math or logic puzzles or stuff like that to do. So if we wanted to even increase this, then we're basically going to say draw a line to every single point that you can find. We're saying kind of unlimited radius and unlimited number of points, if that makes sense. So you can use this, animate it around and stuff, and find some interesting results. you limit the distance, maybe the number, go to like 5. Get some interesting kind of stuff happening. So I think this kind of thing, you could even use it as the base for like in effects with the IK, if you were doing like a spider animation or something like that. Sometimes people will do this to generate footprints. You basically have points scattered or footprint points, and then as you move around, those are the locations that you can place your feet at or draw your line connecting to. So that's a little bit more of an interesting way to use these. Another thing we can do, going to keep bringing in stuff from my example template. So this one, I've set it up to do a similar kind of thing. Just have a single point here, and then we have a bunch of points that I've scattered. This randomize, we're making a random PScale for these points. So this is pretty much the same thing as the rand VEX. We've used it before, like that. Is just a high-level node that kind of manages it. It has some other ranges and multipliers and stuff like that that you can do if you want as well. So visualizing the PScale, we have all these points, also just making them blue. And then with this wrangle, I've set it up using the near points function as well. And basically what I've set this up to do is check all of the nearest points and only allow the radius to be as big as the nearest point. So let me, I'm also going to set an alpha on these to make them a little bit easier to see, hopefully. So a little bit more transparent. Could also, if I just go to geometry here, just going to bring up the tessellation level of detail to make them a little bit smoother. So what we're setting up here is a tool, and it will basically always shrink or only limit the radius of the particle or the point so that it's never overlapping or intersecting with any of these other spheres. So you might think, like, why do we need arrays to do this? We could just check the single nearest point. The reason is with certain circumstances, like if we look at this situation right here, it's a little bit more apparent. Just going to move it up. So as I move it over, the nearest point in 3D space is this point. But because we have different scales of radius or different sizes of particles, we also need to check with this point and to be sure a few more points around it. And then I've done some special things in here. We're basically always finding the minimum distance or the smallest bit we're going to be allowed to make our current particle. And then at the top here, this is a little bit of a special way to declare a PScale. What this is basically saying is if the PScale attribute doesn't exist on the geometry, initialize it to 1 or to the default, like the default of the PScale attribute will be 1. This is like if you use the attribute create and you set the default up here to 1. That's kind of what that's doing. So if I set it up here to something like 25, then as I shift over, it will be allowed to go all the way up to 25 for the size. So if you're making some intersection tests or stuff like that, this can be a useful way to make sure that the points that you're placing will never intersect. And I think we can even do it. We like scatter, make a bunch of points. These will always be filling things perfectly. This is really cool. Thank you. Yeah, it's hopefully gives you some more encouragement to delve deeper into arrays. So they are pretty complicated, but hopefully this is making it a little bit more clear. We could step through this a little bit. This function here, I've just done it the same way. Instead of typing this all the way out like I did earlier, near points, I've just done kind of an abbreviation or shorthand. So NPs, near points. This is our array, and I'm only checking the nearest 12 points. But I've just typed in this witchcraft, this devilish, satanic number as just kind of a, to say unlimited, just a very big number. And then with this minimum, I've done another thing. So this is the starting radius or PScale. And as we go through, we're checking each candidate or each one that we find, each point that we find, and saying what's the smallest we have to make it to fit within that particle. So if I just set this to 1, you can see that there's a lot of overlaps or there's some mistakes. But then as we check more and more of the nearby particles, it's easier and easier to fit things in without making any mistakes, if that makes sense. So what we're doing as we iterate through the array using the for each function, the similar code that we've typed in here for the for each, we're finding this PScale or the radius of the nearest point. So earlier up here, we were just looking at the position of the nearest point. Here we're also finding not only the position, but the PScale value, because we need to know that for how big the point is. And then this minimum here, this is going to say whichever the smaller number is of the current minimum value, and then the distance of the current point to the nearest point, and then this subtraction by the radius to basically take into account the radius. Does this kind of make sense? It's a little clear, hopefully. You can go with, it dies. You can go with less points maybe to, let me see if I can get a different outcome that's a little bit more interesting. I don't know. So we're starting our minimum, our counter at a really high number, and then each time we check one of the points, we basically say use the lower, assign min to the lower of either this point or the current value or whatever value it has. And then you end up, or the final result, we set the PScale to whichever is lower. The existing PScale variable or attribute in this case, or the new proposed minimum value that we've calculated. All right. Hopefully this makes sense. I'm going to start moving on. So we'll say scale radius to avoid overlaps. We want to get up to date. Did I lose my shelf? Need to get out of the crash file as well. All right. If you want to get up to date, there's the file I'm working with. So let's keep going a little bit with some of these examples. Another thing we can do, just going to grab another grid. I'm going to grab a few different nodes. Whoops. All right. We're doing a similar thing here with a grid. This one has more subdivisions. It's a higher resolution. And then I've scattered points and using this attribute noise function, just moving them around. This attribute noise function is similar to what we did in earlier weeks. You go inside of it, you can maybe see what it's doing. I guess they're using VEX. But it's doing a similar thing like the X noise or curl noise or that stuff just to move points around over time. Could you calculate the last n, the last number n in the near point function by checking the biggest PScale somehow and calculate the radius of that? See how many points are within that radius. Might be a bit more complex than setting it to 12. I'm not sure exactly. You might be able to. I don't know if it would. I'm doing maybe it might be a little bit too brute force of a method. I'm trying to handle any kind of case. If you do like initially just sort this by PScale, you might run into a situation where you have a small point that's really close that you don't want to intersect with, if that makes sense. We make more like if we go over here, maybe, I don't know if I can't really move these around anymore. Let's take him. All right. So as I move over here, you set it to 12. You might be good. If there's a sphere with a very big PScale, it might fail. Yeah, so I've set it to 12 is kind of an arbitrary number. I haven't put, there's no like mathematical reason to it or anything like that. The 12 is hard coded. Depending on your situation, you could do other things. You might need more as well. Like if I really turn this up quite high, 12 isn't going to be enough. You might have to go all the way up to like really big number, you might start to run into the issues. But yeah, the reason that I was choosing 12, it was pretty arbitrary. And I think because I'm going into negative numbers here, like inverted scale when it goes inside of everything, so it's having some issues. But the reason by picking 12 was like you have one point here that's smaller, a bigger point here that's slightly bigger, and then you keep going. It's a bit too big. Yeah, if you did a step ahead of time to pre-compute how many points you needed to check, you could do an optimization that way. But for the most part with VEX, what I'm doing, I'm a little bit lazier than that. But yeah, there's some nice functions you could do to check stuff ahead of time. You can also look in find shortest path, or not that one, connect adjacent pieces. You go inside of here, they do somewhat similar code here to connect other lines. They use some different functions and stuff like that, but they still use this for each. If you're interested in looking at arrays and stuff like that, they've done a similar thing here inside of this node with this function. All right, so we have our set of points moving around with some noise. And then I'm going to be doing a similar thing here with arrays to find nearest points in the next input. Just going to grab this one line of code, get started with it. So we could set our limit to 5. These are just like thresholds or cutoffs. So like Jonas was pointing out, just to make sure you're not doing too much calculation or whatever. We could set this 15. And we'll just run our loop, say, for each int et. And the array we're running over is nps, and near points. It's an abbreviation. And we'll make our brackets. So what we can do inside of here is set the color equal to the color, or we'll generate a random number from the nearest point number. So we're having some issues because we're overwriting the color value when it finds more than one point. But this is a pretty nice technique where you can generate textures or colors from the nearest point numbers. So if we just set this to 1, this is a little bit more similar to kind of what you've seen before probably. It's like Voronoi noise. You're just looking at the nearest point number and generating the text, the color or the texture from it. So that's pretty cool. We can make it a little bit better. We just make a copy of this here. How is it animating? I've just used this attribute noise up here. So with this one, you can set it to animated. Rumalo, how's it going? Yeah, it's a bit of a, sometimes you could do all this stuff with VEX if you wanted to, but just to keep things clear, like just to introduce 1 or 2 topics in the code, I'm breaking this stuff out into extra things. So we could set this to P. We're adding zero center noise to the position, and animation, you just check the animate. So depending on the settings, you can get different things. What I was saying with breaking this out, like if you really wanted to, you could add the noise inside of here maybe and get some other kind of results, but just to keep things organized, I'm doing it this way. So if we want to start blending the colors together, we could get a little bit more of an interesting result. So right now when I do like 6, you can see we're clashing our colors. We're getting some artifacts or some errors as it just happens to find other points. And then this also depends on the order that your array runs, because we're just overwriting the color, just whatever the last point number it runs over is the one that it will end up with. If you do add, and you can see if we just really go down with the exposure, we're just keep accumulating the color value for each point. So this, again, isn't a good idea. We want to start looking at the distance and then doing some like filtering or some blending of our points to get a better result. So we'll say, let me just call this the sum of the weights. And we'll start it or set it equal to 0. So what I'm going to do here is like a weighted average of the nearest points and then set it up based off of the distance. And should be good with it like this. So we want to find the distance between the current points from this input and then the kind of point that we're iterating over or that we found. So you can say the distance of P and the point position. So you can do it like that. And then that's the distance. So we were doing the same thing up here, I believe. A bit of different like variable management and stuff, but the same thing defines that. So we're using the distance here and then our weight. We can use the smooth function. I'm going to do 1 minus smooth. We're going to do 0. And then this next number is kind of important. It's like the max distance. Just say something like this. I'm going to do this at the top as well. So if we want to use this maximum distance here, then we can also use it here. And then this is the distance value is the value that we want to smooth. And then we're going to add the current weight to the sum or the value of all the weights. So the weighting factor is like how much of the color we're going to be using. And then when we add the color, we can scale it by the weight. And then at the very end, we can normalize our result, divide all of the colors by the sum of the weights. And I think I did something wrong here. So the random function will default to giving you a float because we're multiplying it here by a float. So if we declare it as a vector, then when the random function runs, it will know to generate a color or a vector instead of a float. And then it looks like we're a little bit better. I think I've also done something wrong. I don't know if we need to start this color here at 0. All right. We've done it. So by default, the color will get initialized to 1, and that was causing some problems. So now we're blending the colors between the points. We do a bigger maximum distance, then we can get like a smoother gradient. You might want to increase your maximum points here. This is kind of like what Jonas was referring to, like if you you exceed your maximum points. For this case, we'll start to get some artifacts. So what I usually do is just set it to a bigger number than I'll need, and then it will be able to take into factor as many points as you are considering. You're just basically saying don't allow this to be a limit. So it's hopefully pretty cool. Do a file, keep moving. I'm just going to build off of this same setup and do some other stuff pretty quickly. So if we just do a generate, say this is weighted filter. So if we just do a point cloud generate, we can make 5 points. Can use the attribute noise, and because they all have the same starting position, they'll all get moved to the same destination, but they all get the same noise value. So we can just jitter or randomize them a little bit before we move them around. And then if we do a copy to points metaball, can start to get a blobby, our little lava lamp, something cool like that. Let's also grab our PScale randomizer and use it here so our blobs are a little bit different. And we want to convert our metaballs to polygons. We can just do this convert at the end. Just turn up our divisions. And let's take our point cloud, and we'll just make a color for each point, just random. So again, this is similar to what I was doing here, but we're just going to predefine it this time. So simple, so yet so cool. It's mesmerizing. So we're set up here, but instead of generating a random number, I'm just going to want to pull the color attribute from the geometry up there. You might be able to do a little bit smaller of a distance. And then we can start to get some interesting kind of color mixing or gradients or stuff like that happening. So these points up here have a color, and then using our VEX function. We're going to iterate over all of the nearest colors that we're merging or mixing together, and then use our nice kind of smooth weighted function to blend between them and get a nice gradient. Dude, we're in the lava lamp. So we can also maybe play around with this stuff. Yeah, it's pretty fun stuff. So the reason here to use color like this, if you want to, we can set this up using a wrangle. We could even go grab one of our earlier ones. So like here, we're using the literal array to define like a selection of colors. We can use it again here. Just want to update it to run over points. This is the Terminator. This is like Terminator takes acid and then he does his melt into the fluorescent into a colorful pool. So what I'm going to do here is just predefine a set of colors. So just for the sake of like design, you might want to work with a predefined color palette instead of generating random numbers. So we have red. We could do like red, blue. This one is going to be yellow. And then this is our magenta. We want to make more points. We start to get some that find yellow as a color. We can start to get some interesting stuff going on. Whoa. All right. There's a few more ways to use arrays. We'll move on to the final example now. No need for flip. You can actually do kind of similar interesting stuff with flip with this. So like if you were meshing flip, you could delete like a subset of your flip simulation particles and then randomly color them and get some cotton candy or I don't know what you want. This is like you put the Skittles on the stove, on the skillet or something like that. But yeah, you can use this even for meshing flip. A lot of people use it like Photoshop or Illustrator to just give like interesting gradients. Like if you crop in or whatever, you get some interesting kind of like backdrops or whatever. If you have more detailed mesh, you can do that and get interesting stuff. So we'll move on now and try to tackle this final example. It's a little less, should be a little less daunting than some of the previous weeks. So I wanted to spend more time just doing these simple examples of the array utilities today before building on or before tackling this. So now that we're more comfortable with arrays, it should hopefully make a little bit more sense. So if we think about some of the techniques we were using earlier, we were doing the grow lines using noise. This is going to be pretty similar to this, but instead of growing using noise, we can grow the points or move them around using a predefined selection of directions with arrays. So let's just move down here and we can start with generate again. And I'm just going to start with 1 point. Sometimes I do this so we just have an option later to scale up or down and choose how many points we want to run over. So we have an empty VEX code. Let's let's just think about what we were doing earlier for to grow the vines. To grow lines, we were saying for integer I equals 0. This is the current count of our for loop. You got to keep these straight with like, we've been using for each. This is only for arrays, specifically like length or to adapt to the length of your array. This for loop, again, is just a traditional for loop function that you say your initial value, your end result, say 32, 23, and then your increment. So just, usually people are just incrementing by 1 like that. So if we want to use this to draw a line and say int line equals add prim 0 for myself and poly line. So this is the line we're going to attach points to draw it. We're usually doing this to manage things a little bit easier. So I do remove point. So I'm basically deleting the current point and then just using it as our starting position, if that makes sense. So vector pose equals p. It's a little confusing. The reason I do this is basically we don't end up moving ourselves. Like we want to place points exactly where they are. If you keep updating p, your starting point will move along and you'll end up like at the end, wherever you left it at the end of your code. So instead of doing it that way, I make a copy here. And then this is more explicit. Kind of like if you're drawing a line, you like don't pick your pencil up or something, it ends up at the end of the line. This, we're using it more like you're just drawing dots each step. So we make our point position, and then if we want to add the point where we currently are, we can use add vertex. I'm going to add it to the line, and then we just need to add a point where we currently are. This will be 0 and current position. So we're back with the start point of our curve. And then we can start drawing. Let's say pose plus equals. We'll do the curl x noise, like we were doing with the ivy growing example. And we'll just see what we get with this. So each iteration of this loop, we're moving the position a little bit. So if we do these add vertex functions, we should end up with a line. So each time of these 23 steps we increment, we add another connection or another segment to our line. We want it to look a little bit more smoothly. We can multiply the position by a lower number. This is like a lower frequency noise. So we're just allowing our point to move or walk through a noise function and recording the position at each step of the noise. So if we want to get to where we were here a little bit more kind of synthetic or less organic, you can see this is more like, I don't know, sorting board or a pegboard or something like that. little circuits or something that's more digital. The way that we can do that is basically, instead of a curl noise, it's like a nice natural noise function. We could make an array of directions that we want to use for coordinates. So if we take a vector, we'll call it like proposed directions or possible directions. We could use the Egyptian brackets if we want. This is going to be any kind of possible direction that we can travel in. We can start with 1, 0, 0. This is like 1 in the x direction. We can also say 0, 1, 0. And we'll just leave it right there for now. And just take a look at what happens. So if we look up here earlier, to access or to just grab a random entry from this array, we were using this code. So we'll just go ahead and do it again down here. So instead of a curl noise that's a random based off of the position, we'll just say directions. So if I say directions 0, we'll just always move in that direction, which happens to be positive x. If we go the other way, we just go straight up. We can also use this with the random function to generate a unique random number for each segment of the line or each segment of the curve. We can use I, because that's going to be incrementing or changing each time. And like the array is expecting us to give it an integer, an index number. Right now the random number is giving us, it's going to give us a float from 0 to 1. If we just say floor, and then we just scale it to the size for how many possible directions we have. Then we can, each step, it will just pull a random direction that we want to move in or walk in. So we can keep adding directions here. Like that. And then we're only moving kind of in 90-degree angles. Because each new direction we pull, it will always be like this. If you want to, you can add diagonals and get funky kind of lines. But to get this rigid effect that I like, I'm just saying only move in along axis specifically. Don't go diagonally or any other direction. So we've just said you can either move in positive x, positive y, or positive z. Then if we want to balance this out, we can repeat the same axes, but this time the negative directions along those axes. If we want to go really big, Windows pipes, screensaver. Yeah, this is pretty similar to that. So if we go really big, we can start to make some insane structures. And it's pretty interesting geometric kind of forms or whatever. If we want to do some more stuff just to make this more interesting, kind of like I was doing for the animation, instead of using 13 here, or whatever arbitrary number, we could say the frame. It's like a classic thing I was doing before to draw stuff. We can also do with this I right here, if we take the floor of it and you could say the floor of this divided by 6, or some number like that. So what we've basically done with that is say only get a new direction every 6 iterations. So we have a little bit more kind of drawing or stuff like that happening. Does that make sense? It's a little bit of a hack. It's basically saying every 6 steps, we're going to be generating the same random number. We're going to be using the same number to generate a random number. And then like 0, 1, 2, 3, 4, 5 divided by 6 will all round down to 0. Then 6, 7, 8, 9, 10, 11, 12 divided by 6 will all round down to 1. You just keep kind of stepping like that. We could say we don't want to draw the line after a certain length or a certain time or distance. So if we say if I is less than, I'm going to do the frame number minus 12. I think I've flipped this around. I want to do greater than. It looks like, because I still left my start point there, it's always going to be connected. So in this case, I might just want to skip that step. So we can continue on with our pipes screensaver. We're going to make more points. We can do that, but we're running into a similar issue that they're all overlapping. So what we can do is when we generate a random number, we can also just accommodate or add the current point number that we're generating from. So then we start to get unique outcomes. Sometimes you can do like another random from this. Multiply it to, we'll just make sure you're really getting really big different random numbers, if that makes sense. It's like if you use 2 similar of numbers that are all just integer offsets, sometimes you'll get some weird patterns or some weird similarities in your generations. We can continue to make some interesting variations. We can, let's take our, instead of like -12, or we're basically saying draw our lines from the current frame to 12 frames previous. We can multiply this by a random number. So we're going to say random. This one we just want it to be based off of the point number. We could make this bigger just to exaggerate stuff. So some lines that are drawn are going to be really small, some ones will be really big. There's some interesting variation there. What we can also do, say if the if I is greater than the frame. Let me think here. Let me just start with this. So what I'm doing here is adding another point, but not connecting it. So we can kind of get an interesting like history of where things have traveled. And then if we want to do that only when the I is equal to the frame, we can try it like this. Let me see. Let me just make my point size bigger. Might need to say frame -1. All right. So what I'm doing there is just adding a point at the tip of the curves for where we're drawing. We can keep going a little bit, and right here we've hard-coded in just every 6 iterations to make a curve or to choose a new direction. This is another thing that we could multiply by a random seed or a random number. So now some longer ones will go and some shorter ones will move around. If you want to use different geometry as like a starting point, you can use a grid. And this is just kind of your starting positions. We make it really big, really wide. We'll get different stuff. And make more points. Let's get out of that. More points, less points, a ton of points. You start to see what happens. Yeah, it's pretty fun to play around with. It's a kind of difficult challenge to make creating the tool. Just different ways to use arrays, depending on how you want to think about it. You don't always have to use arrays, but working with bigger sets of data and stuff like that can be fun to manage things that way. So it was like last week's example, if you guys remember, we had ended up making an array to hold each thread like that. So if we didn't want to do it, we could have like hard coded in to make just 8 primitives or 8 threads, but as a cleaner syntax and to make things a little bit more concise and flexible, using arrays is a little bit, it's definitely a more advanced coding tool, or I don't know what you want to call it, data type to use in VEX, but it makes things a lot more manageable and flexible. So like with this stuff, if we didn't want to move up and down in Y, you only wanted to move in X and Z, like horizontally, you can just eliminate that, and the rest of the code will adapt to update like that. So yeah, that probably will be it for this demo. We'll do another file share. Getting a ton of different stuff to play around with. This one, I think we can change it to frame if we want to do a similar. So here we're drawing with noise. Here we're drawing in our own direction array. So we're basically saying here noise is specifically designed to interpolate or to kind of rotate around and give you natural kind of like wind blown behavior. And instead of that, we can specifically hard code or define like a rigid list of directions to travel in, and then just alternate them, alternate between them at specific time intervals. So yeah, hopefully it's pretty helpful. It's a pretty technical